Another common question in paper one is about the pH. So the pH is a measure of the hydrogen ion concentration in a solution, and the pH equals, to calculate the pH, it equals minus log 10 of the hydrogen ion concentration. And to calculate the pH, we need to find the hydrogen ion concentration, and we will do that depending on the type of solution. First of all, the strong acids. We have two types of strong acids. We have the monoprotic and the diprotic acids. So monoprotic acids or strong acids in general will fully will dissociate to give the hydrogen ion and the anion or the conjugate base. So if we have a monoprotic acid, this is the acid that will give you only one hydrogen ion per molecule of the acid. The hydrogen ion concentration in this case will equal the concentration of the acid. So because 1 mole of the acid will give you 1 mole of hydrogen ion. So the pH, which is minus log 10 of the hydrogen ion, this will be minus log 10 of the concentration of the ion and of the acid in the solution. Example of that is hydrogen chloride and nitric acid. The diprotic acid, something like sulfuric acid, where each mole of the acid will give you 2 moles of the hydrogen ion. In this case, the hydrogen ion concentration will be 2 times the concentration of the ion. Again, you can calculate the pH as minus log 10 of 2 times the concentration of the acid. Example is the sulfuric acid. And then we have water. So water as well partially dissociate to give the hydrogen ion and hydroxide ion. And that will allow us to calculate what is called the ionic product of water. Ionic product of water is a constant value for water at a certain temperature. So at certain temperature, the ionic product of water will be a reflection of how much of the water molecule has actually ionized to give the hydrogen ion and hydroxide ion. Ionic product will equal the concentration of the hydrogen ion times the concentration of the hydroxide ion. Sometimes they ask you to calculate the pH of water at certain temperature. They will provide you with the ionic product of water at that temperature. In this case, to calculate or to find the hydrogen ion concentration and the pH. So the neutral water, the hydrogen ion concentration will equal the hydroxide ion concentration, and both of these will equal the square root of the ionic product at that temperature. So the pH can be calculated as minus log 10 of the hydrogen ion concentration. So if you can find the square root of the ionic product, then this is going to be the hydrogen ion concentration, and you can calculate the pH. We can calculate the pH of a strong base using the ionic product of water, because when you use a strong base like sodium hydroxide, it will dissociate completely in water to give you the metal and the hydroxide ion, or the cation and the hydroxide ion. And now if we have a certain base like sodium hydroxide, which has a certain concentration like this one, 0.02 mole per decimeter cubed, then the concentration of the hydroxide ion will be considered at the concentration of the hydroxide from the strong base. Now we can use the ionic product of water, which equals the hydrogen ion concentration times the hydroxide ion concentration. The hydroxide ion concentration now is not going to be the similar to the hydrogen ion concentration. It's going to be the concentration of the base. So we can find the hydrogen ion concentration, which is going to equal the ionic product of water, which is going to be provided to you in the question, divided by the hydroxide ion concentration, or the concentration of the base. And then you can calculate the pH as minus log 10 of that hydrogen ion concentration. Note that if you have a base like barium hydroxide, where 1 mole of the base gives you 2 moles of the hydroxide ion, then the concentration of the hydroxide will be double the concentration of the base itself. Now, moving on to weak acids. So weak acids partially dissociate in water to give the hydrogen ion and to give the anion. So we calculate what is called the Ka, or the acid dissociation constant, because it's a reversible reaction. The acid dissociation constant of the acid is similar to the constant for the irreversible reaction. However, the only difference here, because the acids are very lightly dissociate dissociate or very partially dissociate in water. So mostly when we put the equation and do the calculation, the concentration of the acid here, which should be the concentration at equilibrium, will be taken as the initial concentration of the acid, because only a small fraction has dissociated to give you the hydrogen ion and the anion. So Ka will equal the concentration of the products of the dissociation, which is the hydrogen ion, and the A minus or the anion divided by the concentration of the acid itself. So normally, if the Ka is a larger value, that means we have more of the hydrogen ions concentration, which means that the acid is a stronger acid. So the pKa and its uses, the pKa, we can calculate the pKa in the same way as the pH, which is minus log 10 of the Ka. The lower the value of the Ka means the acid is stronger. And it's useful for comparison between different acids and their strengths. So the higher the value of the pKa, the lower the value of the pKa means the acid is a bit stronger. And then how to calculate the pH of a weak acid? Now we're going to use this equation. We're going to use the Ka value, which is going to be provided to us in the question. And we're going to have also the concentration of the weak acid. So now we can calculate the concentration of the hydrogen ion, because the concentration of the hydrogen ion will equal the concentration of the anion. Now we can put the equation as Ka equals the concentration of the hydrogen ion squared divided by the concentration of the weak acid. And then by rearrangement, the concentration of hydrogen ion will be the square root of the product of the Ka times the concentration of the weak acid. And then finally, pH will be minus log 10, the concentration of the hydrogen ion. So titration and the pH curve is very common in the exam. In 2024, there was a whole long question in paper 3 about the pH curves. So pH curve is when you do the titration. So here you can see that it's titration of the of a strong acid with a strong base. And then with each addition of the titrant, which is the base in this case, you're going to measure the pH of the solution. So it's a curve of the volume of titrant over versus the pH of the solution. As you can see that the pH starts to raise slightly until we reach a point where there is a massive change in the pH with a very small addition of the base. This is the vertical part of the curve, where this is the will give us the equivalent point, or the center of this vertical part will be the equivalent point or the end point of the titration. So these are the different shapes of the curve, the pH curve, based on the type of the acid and base we use for the titration. So if you use a strong acid with a strong base, you can see that you start off with a pH around 1 or 2, and then the nearer the pH 4 or 5, there will be a massive change in the pH with the small addition of the strong base, where the equivalent point will be around 7 here, and then the pH will increase until we reach around 12 or 13 with the excess of the base. And if we use a strong acid with a weak base, like if you use HCl with nitric acid, with ammonia, then you're gonna have a start again at 2, and then you can see that there will be also a bit of a change here in the pH, bigger change in the pH nearer the end point when we start to do the complete neutralization. And then the pH will increase here. So the maximum pH will be around 8 or 9, and the endpoint, it will be around 5, pH 5. And then if we use weak acid with a strong base, it's going to be similar to the other one, but now we start at around 3 or 4, and the pH will, at the equivalent point here, would be around 9. And finally, the weak acid with a weak base, wouldn't be this massive change, so they don't have this vertical line if we use weak acid and weak base. The same will apply for the titration of a base with an acid, but the curve will start from the high pH and go until the low pH, because you are adding acid to a base. So it's very important to choose the right indicator for the type of titration we are performing. This is because each indicator has a certain pH range where the sharp change and the color take place. So we have two indicators. The first one is the methyl orange, and methyl orange usually change its color between 3.5 and 4.5. So if we have the end point, or if we have the vertical line passing through 3.5 and 4.5, we can use the methyl orange as an indicator. Otherwise, if it doesn't, then that means the indicator will change its color before the endpoint or after the endpoint. And then we have the phenolphthalein, where it changes its color between around 9 and 10. So for phenolphthalein, if the vertical line passes between 9 and 10, then it would be a good indicator to use. So when we look at the different types of the pH curves, you can see that for a strong acid and strong base, the vertical line will pass through both the methyl orange and phenolphthalein. So you can use any of these two as an indicator for this type. But when we use a strong acid with weak base, titration of a strong acid with a weak base, then you can see that actually the methyl orange will be the best one to use, because the methyl orange will, the vertical line will pass through the pH range of methyl orange, or methyl orange will change its color during the end point or when we reach the end point. However, the phenolphthalein, we would reach the endpoint and the phenolphthalein wouldn't change its color. So the range is beyond the range of the vertical line here. And if we use the mix of a weak acid and a weak base, neither of them can be used. So we cannot use a specific indicator. There will be no charge, no distinct change in the color at the endpoint. In this case, you only can use the pH meter to calculate, to find the endpoint for this reaction. You cannot use these indicators. Finally, when we talk about pH, we have to talk about buffer solutions. So buffer solutions will resist the pH change on addition of a small amount of an acid or a base. So what's the buffer solution? How is it made? It's made of a mixture of a weak acid and a salt of the conjugate base of that weak acid, like acetic acid, or ethanoic acid and sodium ethanoate, for example, or it can be a weak base and one of its salt, like ammonia with ammonium chloride, for example. How does it work? We have the acid, and we know that the acid will partially dissociate in aqueous solution to give the hydrogen ion and the anion. And then we will add some of the conjugate base or of that anion to this acid. So when you add a little bit of an acid, or when you add some acid to the buffer, what will happen is that the reaction will be shifted to the left-hand side to compensate for the excess acid, or the acid that is added will react with the anion. The anion here is going to be in excess because you added the salt, or you added the anion along with the acid. So we have the acid in excess, and we have the ion here, the anion in excess. So if you add a little bit more of the acid, then the excess acid will react with the anion. And that will resist the change in the hydrogen ion concentration, basically. And if you add some base, the base will then react with the acid, and that will shift the equilibrium to the right to produce more of the acid. So you will get more of the acid to balance the pH again. So now this is how it works and how it resists the changes of the hydrogen ion concentration or in the pH. So how can we calculate the pH of the buffer? Again, we're gonna use the Ka value, or the dissociation constant for the acid. So the Ka will equal the hydrogen ion concentration times the anion concentration divided divided by the acid concentration. In this case, the anion concentration will be the concentration of the salt that we added or the conjugate base that we added. So if we are using ethanoic acid with sodium ethanoate, it's going to be the concentration of the ethanoate. And then the HA, this is the concentration of the acid. This is the original concentration of the weak acid as well. Now we can calculate the hydrogen ion concentration by rearrangement. So it's going to equal Ka times the concentration of the acid divided by the concentration